Okay, so we have seen how a solar PV cell operates, right? How it absorbs solar radiation, gives rise to an electron hole pair, which then gets swapped away because of the depletion their electric field, and which results in the production of electricity, right? So in this video, let us have a continuing from there. Let us have a look at what is the electrical characteristics or the electrical behavior of a solar cell. So as we discussed, this is a solar cell, and let's say this is P layer, this is N layer, and this is the depletion region, right? And if I'm able to tap from both sides, uh, this is how the solar cell is, and this is how a conventional PN junction also looks like, right? At a higher level. So if I consider this as a PN junction, and if I try to write equation for a PN junction diode, let me consider this as the current that is going in, and this is the voltage drop across the diode. Then the diode equation I can write as I is equal to I naught e raised power qv by kt minus 1, right? And so this equation you would have seen being derived in your basic devices course. So if we plot this equation in IV characteristics, then this is how it roughly translates to, right? This is how this equation looks like. At zero current, you can check the voltage is zero, and as the voltage approaches minus infinity, the current is minus I naught. So in this equation, if you see, I naught is called as the saturation current, right? Or rather a reverse saturation current, which implies that if you give a negative voltage, a very large negative voltage, before obviously it breaks down, if you give a voltage which is less than the breakdown voltage but large enough, then the current that flows is the reverse saturation current. Q is the charge, K is the Boltzmann constant, and T is temperature in Kelvin, right? We as we understand, the value of kT by Q at 300 Kelvin temperature is nothing but 25.85 millivolt, right? And this kT by Q, since it has the same units as that of the voltage, we call it as a thermal voltage. All right, so far so good. So this is how a diode, conventional diode is. But now what has happened is, in this conventional diode, we have exposed this diode to light, and it has all the phenomena that we have discussed in the previous video happening. So photons getting absorbed, giving rise to electron hole pair, electrons free to move in the conduction band, get swept away because of the field and producing current. So let us see how this basic equation changes if we include all of that phenomena. Yeah. So the same PN junction, right? And this being the current, this being the voltage. And if you see, the internal field is in this direction, right? Because here you have positive charges in the depletion region, and here you have negative charges in the depletion region. So the internal field is in this direction. So if light falls on this and the photon gets absorbed, the photon is of energy higher than the band gap, it gets absorbed, it produces a free electron in the conduction band, the electron E would move in this direction, and therefore it will force a current to flow in the other direction. Right, I've used a subscript L. So what I mean by capital IL or small il is the light generated current. So it's still behaving as a diode, a PN junction, plus there's an additional phenomena because of the photon absorption and the current which is happening, which is being represented by this current IL. So how do I represent it? If you see, this is how I can represent it in terms of equation. So the original equation was I is equal to I naught e raised power qv by kt minus 1. Now I have another component which is capital IL, which is reducing the current. So I can write this minus capital IL. And this becomes the equation of the diode plus the a solar photovoltaic effect that is happening in this PN junction. If you see, this can also be represented as this. So this diagram can also be shown as this is just the diode, and now there is another parallel phenomena, that is this light generated current that is happening, and this becomes the net I versus V. Right, so if I plot this top equation in the same graph, this is how it would look like. So earlier the dark equation was, let me use black for the dark equation, which essentially implies there is no light falling on this junction. So this is for dark scenario, and now this is the one. So what has happened is I and V, everything remains the same. I have just vertically shifted the whole characteristics down. So this is how the everything has changed. Right? This is how the new characteristics looks like. So this is the characteristics of a solar cell. Right? It's for convenience, if you see here now with the polarity of I and V that is shown as per the top figure, you see the current is going in and the voltage is positive. So if both I and V values are positive, that essentially implies the power is being absorbed by this system. This system, when I say system here in this context, I mean this diode plus the light generated current. So therefore in this figure, if you see, if you are in first quadrant, the power is getting absorbed by the system, right? Second quadrant, there is no characteristics. Third quadrant, again power is getting absorbed in the system. It's only in the fourth quadrant where power is being produced. Why? Because either one of the V or I is negative, and therefore the net power is actually flowing out of this PN junction and not coming in. Usually people prefer to represent this graph in a flipped manner. So the usual convention is that if we have PN junction, right, depletion region, then usually people, if it's a solar cell, we would most of the literature would refer the current going out as positive. So let me call it as a PV current, and the voltage still polarity is PV. So if I convert the equation number 1 from the earlier convention to the new convention, then I can rewrite equation 1 as, now the only thing that changes is IPV, which is nothing but equal to minus times the original current I. So if I just substitute I from equation 1, I get minus I naught e raised power qv by kt minus 1 plus IL, right? And now if I plot this new characteristics, it's nothing but a mirror image of the first one with respect to the horizontal plane, right? If you take the mirror image, this is how it will look like. So this is how the, not done anything, I've just taken the mirror image with respect to the horizontal axis. So this is my IPV, and this is my V. For any future discussion in this part of this course, this IPV is nothing but we'll just call it I, because this is the convention we'll be following for solar cell or solar panel or solar module. The current going out of the P side is positive, and the voltage across P is positive with respect to negative. That is the convention reference directions we would be using for solar cells. Okay, so we have got our PV equation, which is I is equal to IL, light generated current, minus the diode current, which is I naught e raised power QV by KT minus 1. Now there is, if you see the diode, again this is an ideal diode equation. If you take a more practical diode equation, then you can add a small n, right? It becomes e raised power QV by NKT minus 1. Right, so where n is the non-ideality factor, which usually goes between 1 and 2. In addition to this, there are a few more non-ideal behavior that exist in a solar cell. And one of that which does impact our characteristics significantly is the presence of resistances. So if you see, again I will draw the simple diagram showing PN junction. So you realize now these wires, the one I have shown on the top and one I have shown on the bottom, when they connect with the silicon material, there is a potential, there is a voltage drop in that junction, in that connection. Plus these wires will also have a resistance drop. Plus when the current flows vertically in this P junction or in this N junction, in this P region or in this N region, still there is a voltage drop. So all of that put together, we can usually represent it as a series resistance. Right? Further, when we talk about this PN junction, the natural process is happening, but there could be leakage due to maybe current flowing in the surface and so on, right? And that could lead to flow of some leakage current through this shunt resistance RSH. So this resistance and shunt resistance are present because of the non-ideal behavior of the system. So what we can do is our original equation, which I'm marking is as equation number 2, the original equation 2 can be converted into this new equation, which shows the equation including the behavior of series and the shunt resistances. How to do that? Let's say we can use basic circuit analysis. Let me call this as V2, the current going out as I2, the original voltage as V1, the current coming from the junction is I1. Right, now I can write the relationship between I1 and I2. I can say V2 minus V1 is nothing but I2 times RS, and I can also write this is, so this is essentially Kirchhoff's voltage law across the series resistance, and I can also write Kirchhoff's voltage law across the shunt resistance, wherein I can say I1 minus I2 into the shunt resistance is nothing but V1, right? And my original equation between I1 and V1 is I1 is IL minus I naught e raised power q V1 by KT or NKT minus 1. Now if I substitute, I need to substitute V1 and I1 in terms of V2 and I2. This equation I can quickly use, and I find V1 is nothing but V2 minus I into RS, right? So this I can substitute into the V1, right? I need to find I1, so I use the other equation, and I can write I1 is nothing but V1 by RSH plus I2, wherein V1 by RSH I can write it as V2 minus I2 RS upon RSH plus I2. Right? So now I can substitute value of I1 from here and value of V1 from here. So the resultant equation that I will get is something of this form. The net current, let me still use the same symbol, I2 is nothing but IL minus I0 e raised to power q times V2 plus I2 into RS upon KT minus 1 minus V2 plus I2 into RS upon RSH. Right? So if you see, this is a more detailed equation incorporating the series and the shunt resistances. Now, what is the effect of the series and shunt resistances? It's something like this. Just to visualize you, let's say this was the original IV characteristics. Now, because of the series and shunt resistance, the values may sort of come in, and moreover the overall, it might sort of come inside, right? This is a very broadly speaking the effect of series and shunt resistance, right? So it'll sort of shrink the whole active area, right? That's roughly the effect this series and shunt resistance would have. And now if you see what is the electrical equivalent circuit, the electrical equivalent circuit of a simple solar cell is this: series resistance, shunt resistance, diode, and light generated current, which is represented by a current source. This is the electrical equivalent circuit. This is the electrical equivalent circuit of a solar cell. Alright, once we have the electrical equivalent circuit, let me just quickly redraw it again. Now I'll just call it I and I'll just call it V. So let me draw I versus V. And since we understand that the positive power is only in the first quadrant, for the time being I'm only drawing the first quadrant behavior between I and V. Right? Why? Because power is only positive in the first quadrant. Other quadrants, it's actually negative. In the next video, we will talk about what happens if the power is negative and so on. So you can watch the next video if you want to understand more about that. For the time being, let's also only consider the positive part because that is the one which we really want to use. That is the one where really solar cell produces power. Let us define some of the parameters in this graph. For example, we can, for instance, let's, this is, what is this? This is the current that will flow from the solar cell if the voltage across the cell is 0. What does it mean? If you have a cell, right, and if you short circuit it, if you force the voltage to be 0, then what is the current that will flow? Let's just call it I short circuit, right? What is the point here on the x-axis? That is essentially when the current is 0. That means if you have a panel or if you have a cell and if it is open circuited, then whatever voltage it will produce, that is the open circuit voltage. So let's call it VOC, right? So ISC, short circuit current, and VOC is the open circuit voltage. What else? Now you see, if I can, what I can do is I can extend this, and I can, using this IV characteristics, I can plot PV characteristics. So what will be the power output? P out is nothing but instantaneous value of current multiplied by instantaneous value of voltage of the panel, right? So I can extend this plot and draw a P versus V plot here, P versus V. So for example, if I take this first point, right, then the voltage is very small, although the current is substantial, but the power is small. As I'm moving towards right hand direction from this side, my current is more or less the same. You can see current is more or less flat, the voltage is increasing, so the power will continue to rise. If you see again, if I'm operating at the open circuit voltage, although there's a substantial voltage, the current is zero. That means the power is again zero. So there is a point where actually power hits the peak value and then again it starts reducing. So this is how the power versus voltage curve would look like. You can use MATLAB or Scilab or any other plotting tool, and you can use this equation, let me call it equation number 3, or you can simplified equation number 2, right? And this is a current voltage equation. You multiply that current with the voltage, so you get a voltage versus power equation. So you can plot that voltage versus power equation, right? And you can see yourself if you get a curve similar to the one shown here. Alright, so this is power versus voltage equation. So now I can define some parameters with respect to this also. So let me call this point as the P max. Let me use blue color. This is P max. I can also sometimes refer it as PMPP, where the subscript MPP denotes power at maximum power point, or MPP. So this point on the top is essentially what we call it as MPP, that is stands for maximum power point. With that we can say, okay, if this is the maximum power point, the voltage that appears at this maximum power point, we'll call it as VMPP. So VMPP is the voltage at MPP point, and whatever is the current that flows at this maximum power point, let me call it as IMPP. So IMPP is the current at maximum power point. So I've defined open circuit voltage, short circuit current, VMPP, IMPP, and PMPP or Pmax. One more factor which exists, which is called as the fill factor. One more definition, right? Fill factor, FF, which is described as the multiplication of VMPP into IMPP, which is nothing but the maximum power, which is nothing but equal to PMPP, divided by V open circuit upon I short circuit. What does this fill factor shows? If you see in this figure, the fill factor is nothing but shows the ratio of this shaded blue region with respect to the this outer boundary defined by this brown color, right? So fill factor is nothing but ratio of this area, let me call it as A1, upon the overall area, which let me call it as A2. So why is fill factor so important? I can understand open circuit voltage is important. Fill factor has a relevance because it sort of signifies or implies how much of the short circuit current and the open circuit voltage capabilities are actually being used in producing power. So for instance, if you produce a cell, or if you have a cell which has a very large value of open circuit voltage, but it has a very poor fill factor because of the series resistance, shunt resistances, and so on. So then the effective power that we will generate is nothing but fill factor multiplied by VOC multiplied by the ISC. So even if you have very large value of VOC and if you end up having a poor value of fill factor, that may not necessarily give you a large value of output power. So therefore this fill factor is a very important parameter while comparing different manufacturing processes, different cell technologies and so on. Alright, once we have defined these parameters, let us see how do they change. Do they change with temperature or solar radiation? So how do these parameters change with cell temperature, for example, with solar radiation? Right. Let's first consider. So there are two main factors here. If you see, one is the open circuit voltage and the other one is the short circuit current. So let's think about VOC and ISC. And let us see what is their effect due to solar radiation and due to temperature. First, with solar radiation, the open circuit voltage changes, yes, but the effect is negligible. Then comes the effect of solar radiation on short circuit current. If you see, what is short circuit current? Short circuit current actually represents the maximum current if you short circuit the PN junction, right? If you remember the original circuit which we have drawn, there is a light generated current IL and then there is a diode, right? And if you short circuit these two things, that means the voltage across diode has become zero. That means the current drawn by the diode is practically zero. That means all the current that is flowing in the external circuit, which is the short circuit current, is equal to the light generated current. Now what is light generated current? Light generated current is proportional to how many electron hole pairs are generated, right? Obviously some of the electron hole pairs would recombine and may not really participate in this phenomena, but it's proportional. So if the solar radiation doubles, right, with the same composition of the photons, so you have the same photons, the composition within the spectrum remains the same. If you have one sun, let's say now somehow you have another sun, right, so you become two sun. So solar radiation has doubled, because of which double number of photons can be absorbed almost, right, because of which almost IL value will become double. So ISC is more or less proportional to the solar radiation, right? It's almost proportional to the solar radiation. It's proportional to the electron hole pair that gets generated because of light, which is proportional to the. Therefore, if you go and if you have a look at any solar panel data sheet, then you would see that they would have shown you IV plots for different values of solar radiation, and you can see the VOC will also reduce, but very slightly, almost the same, but there is going to be proportional change in short circuit current. So if let's say this is for a radiation of 1000 watt per meter square and this is for 500 watt per meter square, so it's almost double. Right, this is the effect of solar radiation. Let's come to the effect of temperature. Now with temperature, the effect on the short circuit current does exist, but I would say it is negligible as compared to the effect of temperature on the open circuit voltage. Right, so as the temperature increases, the open circuit voltage reduces, right? So it has inverse relationship. When I say inverse, not necessarily one upon that, but if one of them increases, the other one reduces. And therefore now if you open and search for any data sheet and it shows the effect of characteristics due to different temperature, you will see a graph something like this. and this is, you will move inside as the temperature increases, because the open circuit voltage is moving inside as the temperature is increasing. And that is the reason why we say that at higher temperature the solar cell becomes lesser efficient, because the open circuit voltage reduces, current remains the same. Assuming ballpark fill factor does not change much, then the overall power that you would get reduces. So the efficiency reduces as the temperature increases. And in fact, this is one of the reason when we discuss about solar panels mounted on water bodies, right? Because the water bodies has a large energy capacity, they can ensure relatively lesser temperature as compared to the ambient air, and therefore the same panel mounted on a water body might give you higher output power for a given radiation as compared to that mounted on the land. You can also plot P versus V graphs, right, for both of these scenarios. So you see in P versus V, if this is how it looks like for 1000 watt per meter square, then roughly the power will become half at the maximum point, right, and it will become half, almost half of what you are getting here. So this 1000 watt per meter square is the solar radiation, right? Let's say the panel has an efficiency X, so then what you get output is 1000 watt per meter square into X upon 100, right? So here radiation becomes 500 watt per meter square and the efficiency is X, so your output power also reduces almost. If you see, almost the open circuit voltage does not, the MPP voltage does not change much. Current MPP certainly changes, but the voltage MPP does not change. On the other hand, in this right hand side scenario, if I draw P versus V, then what you would realize is that the power is reducing and so does the MPP voltage also. So there is a significant shift that happens in the MPP voltage as temperature increases. So therefore MPP voltage does depend on the open circuit voltage, or it does depend on the temperature much more than what it depends on the solar radiation. Yeah, you can keep a note of it. This will come a little bit handy when we talk about the maximum power point tracking algorithms and so on.